So we're going to hear from Jan Bobolz.
Microphone also works. Okay. Okay, good. Cool. Hi. My name is Jan Bobolz. I'm going to talk about how to prove that Groth16 is universally composable. This is from our TCC paper that we wrote with Puya Fashim, Markus Kohlweis, and Akira Takahashi, and myself. So, what is when we say we want universal composability, what do we actually mean? In UC, we express the security of non-interactive zero-knowledge proofs as follows. We have a real world, we have an ideal world, and we have an environment that's the same in both worlds, and the environment is trying to distinguish these two worlds. So what's happening is in the real world, the environment talks to a real prover, talks to a verifier, and to some sort of adversary. And then all of these have access to SCRS because we're interested in Groth16. In the ideal world, we have an ideal functionality that kind of tries to express the ideal version of a non-interactive zero-knowledge proof. So this is supposed to be like secure by definition. And then in the ideal world, we also have an ideal world adversary, which is the UC simulator. Yeah. And then in its head, the UC simulator can basically run the CRS from the real world. So the CRS vanishes from the real world and gets to the ideal world, which the UC simulator can run in its head. Okay, so what happens if the environment instructs some party in the real world to create a proof? That party would just run the Groth16 algorithm and return the proof. In the ideal world, we need to express what it means to like ideally compute a proof, and this ideal way is just to simulate the proof without the witness, giving us that all of the proofs generated in the ideal world are independent of the witness. If the environment tells us to verify a proof in the real world, that would just run the Groth16 verifier. In the ideal world, we are basically taking this proof, asking the UC simulator to extract, and say, okay, this proof can only be valid if this has been extracted correctly, so if there is a valid witness behind this, or if it has previously been output by proof. Of course, we're interested in, okay, and then the whole point of this is the environment is not supposed to be able to tell whether it's like talking to the real world with the real Groth16 protocol or to the ideal world where everything is simulated and extracted. Of course, we're interested in Groth16, so we can never reach that level of security. We don't have like strong simulation extractability, but we can do weak simulation extractability, meaning that we allow the simulator to say, hey, I'm recognizing this as a basically re-randomized version of a proof that I've already simulated. And if it says that, and it actually, this proof has been simulated before, then we don't force it to give us a witness. Okay, so this is what we're going to prove, that these two worlds are indistinguishable for a suitable version of the UC simulator. How does this work? Well, simulation is rather simple. We just use the CRS trapdoor. Remember, the UC simulator just runs the CRS in its head, so it can set it up so that it knows the trapdoor, so that's easy. Extracting proofs will be difficult, and this is what this talk is essentially about. So if we want to extract from Groth16, what are kind of our choices? We can take one of the first three strategies. So we can do a proof in the generic group model, algebraic group model, or under knowledge assumptions. The nice thing about this is we know how to prove Groth16 secure in these settings. The not so nice thing is that we don't really have good models for making these things work universally composable. So there are some models in UC that model, like, for example, the AGM and knowledge assumptions, but they turn out not to be suitable for non-interactive zero-knowledge proofs. And they also point out a bunch of inherent restrictions that the AGM has when it comes to composition, even outside of UC. We could do another way, which is what people usually or often do if they want UC security, which is they say, okay, let's do encrypt then proof. So we are doing extraction with the CRS by just decrypting. And then we can basically run a compiler that will give us a proof system that's based on Groth16, but does this additional overhead stuff. This is good because we can model this in UC nicely, but I mean, it comes with overhead. It's not Groth16 anymore, it's Groth16 plus more overhead. We also have a similar thing with the random oracle model in like a Fischlin kind of style extraction, which we also know how to model in UC, but again, it's overhead. The prover is less efficient, the verifier is less efficient. We could do rewinding, but this checks none of the boxes. So. And as usual, if you have, sorry, as usual, if someone tells you, gives you such a table, you should expect that our goal is to make one of these rows just green check marks. And what we are going to do is to make the first row work. So we want to use the generic group model, and what we'll have to do for this is to make the generic group model work in UC. Okay, so let's take a look at what this would look like. Basically start with a naive version of this. So we can model the generic group as an ideal functionality, and a UC ideal functionality, which is rather simple. It was basically remember this like encoding function tau, which would send group elements to some random encoding. We have some generator, and then because all of the group elements are randomly encoded, the parties can't actually do group operations themselves. Instead, we give them access to this oracle, the operation oracle, which takes two randomly encoded group elements, decodes them, does the group operation, additive in this case, and then encodes the result again. Okay. So this is a way of writing down the generic group model. And then what we could do is just, okay, let's treat the generic group just like the CRS. So we say, okay, in the real world, these parties also have access to this generic group, in addition to the CRS. And then in the ideal world, this simulator basically gets to take over the generic group. This would work, in particular, when it comes to extraction, when the UC simulator is asked to extract such a Groth16 proof, what it can do is just like look at all of the group operations that the prover or the environment or anyone has done that led to these group elements, and basically then analyze, okay, like this is how this group element was computed. So these are kind of the coefficients of the CRS elements, UI, VI, and then these elements are essentially our witness. So this is how the simulator could extract in this setting. The downside, why this paper exists in the first place, is that if we follow this modeling, then similar to a CRS, we would expect that every single protocol would use an independent CRS, or in this case, an independent generic group. So basically, we only have a proof in the setting where every protocol uses a different group, which is, of course, not what's happening at all. Everyone uses the same 2 or 3 groups in practice. So this kind of proof is kind of not that meaningful. Okay, so what do we do about it? We are going to basically come up with a better model in UC for the generic group. And we will call this the Global Observable Generic Group Functionality, GOGG. And the idea will be that this functionality will be global, meaning that it will be shared by many different protocols. How is this modeled? This would mean, so this is basically the old picture. If we want to say that this generic group is used by many different protocols as well as our own protocol, there's an easy way to model this in UC, because we already have an entity that represents all of the other protocols, and that's the environment. So what we can just do is say, okay, the environment also has access to this generic group. As a consequence of this, the UC simulator, as a consequence of this, the generic group doesn't vanish in the ideal world into the UC simulator, but it's now like it's an additional thing that's still there. If you think about it, this makes a lot of sense, that the UC simulator doesn't just get to completely take over simulation of the generic group, because like imagine that we have two different protocols, both of them are like non-negative zero-knowledge proofs, and both of them the extractor needs to completely take over the generic group in order to extract. That would not work. We couldn't put these two protocols into the same scenario or into the same composition and still claim security, because either this one is secure or this other one is secure, but we can't give both of them total control over the generic group. Okay, but we can write this down, we can model this. So this is the global generic group model, essentially. Now the question is, what happens if we do this? We just take the functionality that I showed you and run the ideal world. Now the question is, how can the UC simulator extract? And the answer is it can't. So the problem is that it used to be that the UC simulator just looked at all of the group operations that happened, but now the UC simulator doesn't get to see all of them because the environment can just do queries without the UC simulator seeing them. So the issue is that there's a very simple attack against this where the environment just computes an honest Groth16 proof and gives it to the NISIC functionality. That thing would ask the UC simulator to extract. UC simulator would have no clue how these group elements were computed, so hence no information about the witness, hence no chance to extract. So we need to fix this. One way to fix it is to say, okay, obviously, there needs to be some mechanism by which the simulator can actually see group operations. So let's add this just to the functionality. So this is the fully observable global generic group, which is the same as before. You can still do all of the group operations as before, but there's now this public observation list, which allows basically everyone to read. And whenever a group operation is happening, we just remember in this observation list that this group operation has happened. Okay. So the good news is that the UC simulator can extract in this scenario, because it can just, when the environment does this attack that I just mentioned, it computes the proof. It didn't see these operations, but it can look at the observation list and then see, this is what the environment did. And then do the standard extraction stuff. The bad news in this part is this is obviously, maybe not obviously, but it's way too strong. We don't get any zero knowledge anymore, because what the environment can also do is just look at this observation list and check, the environment could ask, hey, please give me a proof, and then could check in the observation list, okay, how has this proof been computed? Has it been computed? Does it look like it has been computed using a witness, or does it look like it has been computed using the trapdoor? And these things will look widely differently in the observation list in the trace. So basically, this model is good for observation. It's good for extraction. It's not great for ZK. If you like, you can also think of it as the environment is sort of also able to extract the proofs. Like everyone's able to extract the proofs because everyone has access to the observation list. So we can't have zero knowledge. Okay, so if we summarize these, we have design challenges which look as follows. In a way, the simulator needs to see all of the group operations, otherwise we don't get extractability. The environment should not be able to see the operations that the simulator makes, because otherwise it can distinguish our zero knowledge. And yeah, at first glance, probably difficult. But if you look closer, there's a way to make this work. And we basically use a similar solution to what has been done for global random oracles, which is we have some sort of partial observability. And we will do some domain separation between different protocols running on the same group. What this looks like specifically is, this is the whole idea of this. Basically also the main idea of this paper. is that every different protocol session, if I have multiple protocols, they all run in different sessions, and UC assigns them session IDs, S. And I will basically say that every protocol session will get a different random generator of the group. That's going to be the domain separation. And then I'm going to say that, okay, what you're supposed to do is just do operations that are based on your generator. Okay, so that's the first bullet point. These are like the legal operations, and those will be not observable. As long as you keep to your generator, you're good. These will not be seen by anyone. And then there are also illegal operations, which is if you are in a different session, if you are in one session and you're using the generators of a different session, then these will be, all of these group operations that kind of pertain to foreign generators will be observable. Just very roughly, this will give us that there's a way for the simulator to evade observation by just being good and only working on its own generators. And still, some stuff is observable, so there's a chance for the simulator to actually extract at the end, which we'll see in a bit more detail. One caveat is there, we don't see all of the group operations anymore. The environment is definitely able to do some group operations that we don't see, but it will turn out that we see enough, kind of. Okay, so in a bit more detail, this is the new functionality. We still have the observation list. Well, it's heavily simplified, but this is roughly the idea of the functionality. We still have the observation list, and now whenever some group operation happens, we check whether this is like a legal group operation. And if it's illegal, meaning that G1 or G2 contains some foreign generator, or it's based on some foreign generator, then this operation will be added to the observation list, which everyone can see. So what does this mean? So in this setup, the simulator runs in session S star, which is our target session, and it represents this protocol. And the trick is basically the environment plays the role of all other protocols. So it's allowed to query the generic group, but only in other sessions, in different sessions, as prime. So we play this through. The UC simulator can do simulations unobserved. So what does it have to do for simulation? The idea is it takes all of the CRS elements and then the trapdoors and then combines them kind of correctly into a proof. All of these can be done on the CRS elements, and all these CRS elements, because we've computed them this way, live in the same generator. So they live in the correct session. So by this rule, none of these operations that the simulator does for simulation are observable. So the environment cannot tell whether we've honestly computed it or whether we have simulated it, because the generic group doesn't give any information about it. The UC simulator also has a chance to extract. So one way to look at this, if you take the stupid attack that I mentioned, where the environment just honestly computes a Groth16 proof, the environment cannot do this in the target session. So at some point, if the environment wants to create a Groth16 proof on our generator, on the generator that is group generator that is assigned to our session, the environment needs to do it from some different session. And basically, this will mean that these operations will be illegal. And this means that they will be added to the observation list. So when the simulator is eventually asked to extract, it will not see all of the group operations that led to this group element. But as soon as there's at least like one part of this group element that is like that's the generator for the group that's interesting. Oh, sorry, that's the generator for the session that is interesting. Then it gets to see all of those. Okay, so this was highly simplified. In the paper, we explain what it actually means for group element G to contain some foreign generator. Basically, we do some bookkeeping with polynomials. So every generator gets a polynomial and a polynomial variable. And then we keep track of what the group operations are, and then we just look at the polynomial representation of this group element to see whether or not a certain generator is in there or not. We also have multiple generators per session, so it's not the simple scenario that I just said, that there's just one generator. We also built in oblivious sampling into the GGM, which I agree should be definitely there. And then obviously these are all pairing groups, which I didn't talk about. But yeah, this is an easy addition too. Okay, so overall our result is that pi Groth16, which is basically just Groth16 in a way that it uses a random generator for the group, which I think might be normal depending on how you think about it, and then use the generic group for operations. And that usually realizes the weak NISIC functionality in the FCRS hybrid model in the presence of GOGG, which is this generic group functionality that I just showed. This in the presence of GOGG means that we are using the UCGS framework, UC with global subroutines, in order to model like global shared functionalities. So in the end, this is essentially in plain UC, but the UCGS theorem gives us a way to still argue about global stuff. We also have some concrete bounds for how many group operations actually, like what is the loss in security. Yeah, so this is essentially what's happening in the security proof for Groth16 is for extraction. Our challenge is sort of that the only things that I can observe are everything that pertains to my session's generators. So I'm missing some of the picture, but it turns out that even if your Groth16 proof somehow uses foreign generators, or there are some foreign generators in it, that doesn't mess up extraction. So there's a careful argument to be made there. On a more intuitive but wrong level, you could say that Groth16 proofs cannot contain foreign generators because that would just mess up the verification equation, which is, let's say, close to true. Yeah, and then for simulation, the challenge is that there's some observability. We must make sure that the environment doesn't see that we've been simulating instead of proving. But this part is easy because the simulator, we just define the simulator such that it only operates on the legal CRS elements. Okay, so as a consequence of all of this, the take-home message, I think, is that Groth16 as is, so without any compilers, without overhead, is UC secure, at least in this generic group global model. So you don't have to have a bad conscience of not using these compilers. You can still work with stuff. This generic group idea should also enable, this is a conjecture for now, but we are thinking about this, should also enable similar extraction strategies, for example, for KZG and then IOPs. Some parts of standard Schnorr proofs, those should all be CUC secure in sort of this model. It comes with some restrictions. So first of all, if you do a GGM proof, generic group model proof, then group operations are kind of only doable with the queries to the generic group model. So there's no circuit to evaluate these, so you cannot prove something about the group that the Groth16 proof lives in. So recursive proofs would become difficult, but those are always difficult for provable security anyway. And then we added this partial observability. Turns out some protocols actually can't really work, even with this partial observability. They become kind of insecure as soon as you have that. We have a workaround for that in the paper that kind of gives a different sketch of a composition theorem that gets rid of this. And that's it. Thank you.
Thank you very much. Do we have any questions? Opa.
Maybe a stupid question, but can you just bypass this completely by just using Groth16 as a verifier of in the VC sense, of a zero-knowledge, other technology zero-knowledge proof?
bypass it in...
Well, bypass your complexity your complexity is because you're trying to use the zero knowledge property of Groth16. But how about just forget the zero knowledge thing? And just go, I'm only going to use it to VC a verifier of another zero knowledge system. And can that composition be proved UC? I don't know.
Yeah, I would assume so. Really the challenge here is to make it work in the, it gets more interesting as soon as you have generic groups. You want to have something where some stuff must not be observable and some stuff must be observable. If you, like in your scenario, you can just make everything observable and everything just works. That's true. That would shortcut it, yes. But then you also don't get zero knowledge, which, I get the point, yeah.
So since you're using different generators for different sessions, is it correct that the SRS also has to be different for every sessions?
Yes.
So do you think there's any hope of reusing the same? So imagine different sessions actually are trying to prove the same statements, the same circuits. Is there any hope of reusing the same SRS?
Not that I have any hope, no. So the issue is that sharing CRSs is always a difficult thing in UC. We have like some results, like impossibility results for global CRSs. And I guess these would extend to this scenario as well. Maybe there's some idea that I don't see yet, but so far we don't have any idea how we would even approach this.
Hi. Can you elaborate more on like the last point on your restriction? Like what protocol cannot deal with the partial observability and why?
So the simple example is Algemal encryption. So let's pretend at some point I need to decrypt some ciphertext that the adversary gives to me. If I can't make sure that the ciphertext actually lives in my session, then I will do group operation. I don't know this. So I'm doing the group operations, I'm applying my secret key to it. But all of these group operations would become observable because I'm doing group operations on kind of illegal group elements. So the issue you run into is that you leak your secret key, which then you lose any hope of security. Now, Algemal by itself is not UC secure in any meaningful sense anyway. You can fix this by saying, okay, if you give me a ciphertext, you need to also prove that the ciphertext is based on the correct basis and everything. Then you can repair this. But yeah, you need to be careful, I think is the message. Yeah.
Any last question? No? Let's thank the speaker once again. Thank you. I remind you all we have now a break, coffee break. You'll see right here outside, and we'll be back at 11:30.